Hi, Support Vector Machines Scholastic Video Book Series Part 2 Nonlinear Support Vector Machines. Support Vector Machine or SVM algorithms are used in classification. Classification can be viewed as the task of separating classes in feature space. For example, here we have two classes, blue class and the red class, in the feature space, feature x1, feature x2. So here we can clearly say that these two classes can be separated by using a hyperplane like this, or like that, or like this, or like this. So this is a case of finding the optimum separating boundary, and also it is called linear support vector machines. In fact, we looked at the linear type SVM in part 1 of our SVM lesson series. Here in this lesson we are going to look at an example like the one given below, like this. In this case you can see clearly there is no clear separating hyperplane between the red class and the blue class. So therefore we need to find out a method of separating them. In this case we are going to use nonlinear support vector machines to do that task. Let's see how are we going to do that. First of all, let's try to understand the vectors here. In this case we have the blue class vectors 1 1, 1 minus 1, minus 1 1, minus 1 minus 1, 1 minus 1. So basically these numbers represent the features. Feature x1, feature x2. Feature x1 has a value 1, has a value 1. x2 has a value 1. So minus 1, 1. Similarly for the red class we can get the feature vectors. Feature x1 equal to 2, feature x2 equal to 0. Likewise we can get the coordinates of all the 4 points in this red class. Okay, now we need to find a nonlinear mapping function phi which can transform this data into a new feature space where a separating hyperplane can be found. Let us consider the following mapping function. Phi x1 x2 6 minus x1 plus x1 minus x2 squared 6 minus x2 plus x1 minus x2 squared if x1 squared plus x2 squared is greater than or equal to 2. So this is the mapping function for the points that lie outside greater than 2. Otherwise it will be the same feature vector. Basically if you look at the tasks ahead, we have the blue class which obviously lies in the second condition and the red class lies in the first condition. So basically if a point closer to the red class is available, it should be transformed into a different space. So what we are going to do now is to find out how this transformation is done. So now let us transform the blue and red class vectors using the nonlinear mapping function phi. So this is the nonlinear mapping function, and as we have seen earlier the blue class vectors are within the region inside the x1 x2 are below x1 squared plus x2 squared square root. If you take the value it is less than 2. So these vectors will fall under the second category, second condition. Therefore these vectors will have no change after the transformation. But for the case of red class as we have seen that it is going to fall on the first condition, and then we can find the respective vector after transformation. So basically, if I take the first vector 2 0, so you substitute x1 equal to 2, x2 equal to 0, and substitute these values here, and then you can get the transformed value 8 here. 6 minus 2, x1 equal to 2, x1 equal to 2, x2 equal to 0. 6 minus 2, 2 minus 0 squared, and similarly x6 minus x2, x2 equal to 0, plus x1 equal to 2 minus 0 squared. So now simplify. 6 minus 2, 4, plus 2 times 2, 4, 4 plus 4, 8. 6 minus 0, 6 plus 4, 10. This is the transformed vector of the original vector 2 0 using our mapping function. Similarly, you can do it for the next vectors 0 2. This will become 10 8, minus 2 0, 12 10, 0 minus 2 become 10 12. So what are we going to gather from these outputs? Let's see. Basically, we applied this transfer function or the mapping function for the points 2 0, 0 2, minus 2 0, 0 minus 2, and we got new vectors 8 10. So what are they? Where are they? So what we had was 0 2. Basically it is transformed into a place outside the region here. Now we have this point moved to another point here. Similarly, 0 2 point is transformed to 10 8 in the coordinates, and this point minus 2 0, 12 10. Last point 0 minus 2, 10 12. So what we can see now is that we have a clear separation between the blue class and the red class. All the points outside the blue class transformed into a separate place now. So now our problem has simplified into a linear support vector machine problem. So it's a class support vector to classify these two classes using a linear separation boundary. It is very similar to the one that we looked at in our first lesson of SVM. So we can see clearly there is a region in which you can put down the separating boundary. So there is a space between the blue class and the red class. And now we need to identify some support vectors. In this particular case, we will identify 3 support vectors, 1 from red class, 2 from red class, which first one is S1, 8, 10 is the coordinates, and the second support vector here, S2, which is called 10, 8. Basically, we call these points support vectors. They are basically the features, 2 feature vectors, x1, x2, and they support us to find out the boundary. So therefore we call them support vectors. So basically they are the feature vectors from the original red class, which are closer to the blue boundary. So then the third one is S1. So we can include few more if you like, but for this particular case we include these 3. Sometimes we might include 1 or 2 from here to make it more accurate, but in this case we can clearly see that these 3 are quite okay to find out our boundary. So last one is S3, it's 1 1 is the coordinates. Okay, now our task is to find out some parameters, but first of all we are going to have a bias or augmenting the vector in order for our calculations. So basically we had S1 equal to 8 10, S2 10 8, S3 1 1. We will add an extra 1 here into the vector. We basically call it bias input or sometimes augmented input. So 8 10 become 8 10 1, 10 8 become 10 8 1, 1 1 become 1 1 1, and then we call it S1 tidal overtide, S2 overtide, S3 overtide. Let's see how we are going to proceed from there. We are going to find out three parameters called alpha 1, alpha 2, alpha 3, which is again very simple. It's a linear equation here. Alpha 1 times S1 overtide times S1 overtide plus S2 times alpha 2 times S2 overtide into S1 overtide plus alpha 3 times S3 overtide times S1 overtide equal to plus 1. This is a plus positive class. So we have three support vectors. This is for S1, this is for S2, 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 S2. This is for the positive class or the red class. And the negative class, we have a third support vector S3. If you had more than 3 vectors, you can add them down here, but make sure that you have to understand there may be more than 3 alphas in that case if you have 4 vectors, and you need to make sure that you will put a positive one or negative one depending on the type of depending on the support vector, the class that belongs to which class. If it belongs to negative class, you have to put a negative one here. Okay, now we have these 3 support vectors which we found earlier. Now we are going to substitute S1 tidal, S2 overtide, S3 overtide into this equation. So basically we will have 3 simultaneous equations. What we have done here is just basically instead of S1 substituted at S1 is 8 10 1, S1 8 10 1, alpha 2 times S2 10 8 1, S1 8 10 1 plus alpha 3 times 1 1 1 plus S1 is 8 10 1. So similarly substitutes there. This for the red class, plus 1 is here, plus 1 here, and for the blue class also we get the same kind of equation. So we have 3 equations here. Now our task here is to simplify these equations by multiplying them. Okay, here what we have seen just now, there are 3 simultaneous equations. We need to simplify these three equations to find out alpha 1, alpha 2, alpha 3. So first we need to do actually multiplication here. So when you multiply element by element, 8 times 8 64 plus 10 times 10 100, 164 plus 1 165, alpha 1 plus alpha 2, 10 times 8 8 times 10 80, 160 plus 1 161, alpha 2 plus alpha 3, 1 times 8 10 plus 1 19, alpha 3. Similarly we can simplify by multiplication the second equation and the third equation. So here we get 3 simultaneous equations, and we can solve these 3 equations either by using Cramer's rule or by using simple MATLAB program or some other method or manually, and then you can see the values of alphas. Alpha 1 alpha 2 equal to 0.859 and alpha 3 equal to negative 1.4219. So now our task is to find out the discriminating hyperplane. The hyperplane that discriminates the positive class from the negative class is given by this equation. W is the equation of the hyperplane, is equal to sigma of alpha I times Si hat. So these are the alphas, these are the support vectors. So we can substitute the values to find the equation of the hyperplane. Alpha 1 times S1 plus alpha 2 times S. Basically these are S1 tidal overtide because there's a bias here. Alpha 3 times S3 overtide. And then substitute the values of alpha 1, alpha 2, alpha 3. Then multiply 0.0859 times 8 plus 0.0859 times 10 minus 1.429 times 1. You get this number. So we get these 3 numbers now. What we need to know is how these 3 numbers of W represent this graphically. So before we see in graphical form, we need to find out what is the equation of this one. So vectors are basically, we saw that the vectors are augmented with a bias. So bias is the offset or the b. So therefore the separating hyperplane equation can be written as y equal to wx plus b, with w equal to 0.1243, the value that we got, divide by 0.1243 to normalize it to 1, 1. Basically this is the equation of the hyperplane, actually the gradient, and then get the bias or the offset b equal to negative 1.2501, which is the one we got earlier, but divide by the same number, and then you get the offset value negative 10.057. So basically what we got was the equation of the discriminating hyperplane. So which is 1, 1 is the gradient, and the offset it goes through x1 at 10.057. So when you plot a line, drop a line which goes through x1 at 10.057 with a gradient 1, 1 here, so you get the hyperplane. So then we can actually conclude that this is the expected decision surface of the nonlinear LSVM, nonlinear support vector machine. So we use 3 support vectors S1, S2 and S3 to calculate this separating plane. And also we can write a simple code to achieve the same results. So we have 3 support vectors S1, S2, S3, 8, 10, 1, 10, 8, 1, 1, 1, 1, and they substitute this alpha equation and take the inverse of that. Basically this uses the Cramer's rule, therefore the solution will be a little bit different from what we did in the manual case. So we can get the equation simplified and get the values of w hat equal to 0.125, 0.125 minus 1.25. So this is the line shown passing through x1 equal to 1.25 divided by 0.125, which is equal to 10. So approximately it's same because the mathematical approximation gave it to equal to 10 because of this program. Finally we got the same line between the 2 classes, red class and the blue class. So this is our first task, that is we found a separating hyperplane between the 2 classes. Now let's apply this to example, one classification example, and see whether our classification works for an unknown point. So this is the function, transforming function, and let us consider an example where x1, x2 equal to -1, 2. This is a point in the feature plane, and which is obviously, if you look at here, which we took this as the blue class, which is in between 2 and -2. If it is here, obviously we can assume that it belongs to the red class, but what we need to do here is to find out whether our algorithms works and will it be properly classified. So we apply the same thing that we did for the known points, and now x1, x2 is which is what we normally treat this point as an unknown vector. Unknown vector is -1, 2. So if you apply the unknown vector to the transformation function, and again this unknown vector has x1 squared plus x2 squared greater than 2, therefore it will have to go through this transformation, not the second one. If it was a point inside this region, it will be the second transformation. And then -1, 2, we have these values 6 minus x1, x1 is -1, 6 minus -1 is 6 plus 1 plus -1 minus 2, x2 is 2 and squared. Similarly 6 minus 2, 6 minus x2 plus x1 minus x2, x1 is -1 plus x minus x2. 6 1 plus 7, 7 times 7 plus 3 times 3 9, 16. 4 plus 3 times 3 9, 13. So this is the transformed vector of negative 1 2. So we can check the validity of this one and find out whether this is above the boundary or below the boundary. So we can multiply w with the function output of the function here. So basically multiplication of element by element multiplication, 1 times 16, 16 plus 13, 29. So 29 is greater than the line that we got earlier, which is a separating boundary. So that means this point lies above the boundary, so which means it belongs to the red class. So basically we saw the boundary like that. So the point, actually the coordinates, the point 16, x1 16, x2 13. So we can see the point is clearly away from the blue class, so which is quite amazing. This point was quite closer to the blue class. If we didn't do the nonlinear transformation, we will mistakenly identify this point to be, it belongs to the blue class. But now we have this clear transformation function which transforms this point into a faraway point there. So which is actually an advantage here. That means if you get some points cluttered together, and if you can find a perfect function which can transform them into a separate space, separate region, so you will be able to classify using the linear classification algorithms. So what we finally conclude is that this example, the red one, the point that we considered belongs to the red class. Okay, that's an important note that I have to mention in this particular case, because we have used the transfer function, actually the function to do the transformation. What exactly happens is that it will transform the points which are greater than x1 squared plus x2 squared square root greater than or equal to 2 will be transformed, but not all the points will give correct results. We have the blue class, but the red class is outside the blue class, but there are some points that you cannot use for classification in this particular case. For example, I have a small figure here, feature x1, feature x2, but if you have used any of these points in the transformation, you may not get the correct results, or it may not get transformed into the other side of the boundary, so they may misclassify. So therefore please note that for this in this question we should not use any of these points as the points belongs to the red class. So any point out of these dots will be classified. That means feature vectors that lie in all the other regions, including the vectors in negative quadrants, can be classified correctly using this nonlinear SVM approach, other than the points that are indicated here. So that's because of the nature of this classification function, this transfer function. So we need to think of a different transfer function if you want to apply it for this generic case. Okay, that's all about the nonlinear SVM I have today. So if you have any questions or any clarifications, please drop an email. I'm happy to help in case there's a doubt. Thank you.